All right. Hello, everyone. How's it going? My name's Ben. I'm a forward deployed engineer here at Modal. And today we're going to be talking about voice AI and building voice AI apps. People want to say hello in the chat. Tell me where you guys are tuning in from. That'd be cool. Maybe also what voice AI use cases you're interested in, or maybe what you're working on. Those kind of things might help along the way. And while you guys are doing that, I will set up my screen share here. I see a San Francisco. Someone wants to use voice AI to call their grandmother. That's a very noble cause. Hi, George. Hi, Dimitri. We'll give a few minutes for people to show up. But yeah, feel free to drop where you're from and what kind of voice AI stuff you're interested in or working on in the chat. More San Francisco. We've got a Brazil. Hi, George. How's it going? Kevin, Jonas. All right. We have a London, Mexico City. Mexico City, that's somewhere I've always wanted to go. I feel like there's a lot of really good music coming out of Mexico City. Scotland, AI receptionist for small business. Let's see. Hi, Charles from France. We've got someone from Tashkent or no, Sadbek from Uzbekistan. Building a better open router for voice models. That's a really interesting idea. Let's see. User here, Pam AI. They sent a link. I guess we can check that out. People can check that out. More UK. Help Brazilians Brazilians practice English. That's what Kevin said. So like a translation, quite like maybe like a Duolingo style use case. Dimitro from Kiev, how's it going? Seattle, edge cases with potentially poor internet connection. That's a hard one. That's almost, yeah, that's down the stack there. We've got a Tokyo, Japan, brain to mouth. Yoichiro, can you elaborate on what that means? Brain to mouth? I'd be very curious. My background's actually in neuroscience, so once I see the word brain, I'm like, what's going on there? All right, let me add on my screen share. So we're going to do like a whiteboard style thing. I'll be bringing in some images and diagrams, but this way we can kind of keep it fluid because you guys are welcome to ask questions along the way. Can I bring my own LLM for inference, for example, is the first question from Simons. And the answer is 100% yes. That's exactly where Modal shines, right? Where you run your own code in the cloud. And one of the major things people are doing on Modal is serving AI models like LLMs. We'll definitely talk about that. All right, we've got Alexander in Lisbon, really beautiful place. Odyx AI, low latency voice assistance. We will definitely talk about low latency. Translate brainwave to voice. Okay, yeah. So like the stuff they do out of UCSF, there's a lot of work from like Eddie Chang and those folks. Bob Knight also, Berkeley. These are people who so I did neuroscience at Berkeley. And yeah, this is very actually in my wheelhouse. Your Chiro. Maybe we can talk some other time about it. It's a very cool use case. Although getting the data is hard. All right. Unless you mean non-invasive, in which case, then it's a her. Brain to mouth on test flight. All right, cool. He sent a link. I'll check that out later. Very cool. All right. We'll give one more minute, 9:05, and then I'll jump in. Cool. Hi, Willie. How's it going? All right, cool. So let's get started. So to start off here, so we're going to talk about voice AI, and I will, talk about some of the technical details of voice AI use cases when they are deployed on Modal. For those of you maybe who aren't totally familiar with Modal, Modal is a serverless AI infrastructure where you can run your code in the cloud. Sort of the two main products of Modal are functions and sandboxes. So a function is something. Oh, why did it stop sharing my screen? So yeah, so a serverless function, while I pull this back up, I'll explain this to you, is something where you maybe define a little bit of code that you want to run, like say like inference or like speech to text, like you want to take in some audio and transcribe it. And for that, you need some cloud container that has a GPU. Cool. And you don't want to just have some GPU running all the time, or like, your load is fluctuating throughout the day. And so you you don't want to have some steady amount of GPUs, because either you're going to be under provisioned at some point because you don't have enough, or if you have too many, that means during lower times of lower load, you're going to be over provisioned. So you're either going to have bad service or be wasting money. So what serverless functions do is they allow you to scale up and down without thinking about the infrastructure. All you know is that you have this load that's going up and down, and it's making requests that want to run some code, and then Modal will scale the infrastructure to run that code for that many requests. And so for inference, the idea here is, you have a bunch of, say, users trying to transcribe some audio, and all you want to do is think about writing the code to transcribe the audio, and then have the infrastructure scale independently. And that's where the serverless functions come in. We also offer sandboxes, which are more like a normal container in that they're long-lived, and you spawn one up. You create one in Modal. That's the word you would use, and then you can interact with it and run commands on it, and it's a secure container in the cloud. And that's so it's a little bit less ephemeral than a function, but generally they're not going to be very, very long-lived. Like, let's say an agent needs to run some code during a session, it will spin one up. Or let's say you're a company like Lovable, and you need to serve someone's website that they're working on, or that's being vibe coded, but you want it to be secure, you can spin these up. And they're a little bit longer lived, and they have like an identity, unlike a serverless function. All right, so that's modal background. Let's say, so what is voice AI? So for voice AI, the short answer is that these are going to be, inference use cases usually, and they're going to involve speech audio. That's really maybe the most general definition we can think of. The most common use cases are called speech to text, which we abbreviate like this, STT, and text to speech, which is TTS. So they're flipped they're flipped because they are the exact opposite in terms of like what's the input, what's the output. Speech to text takes some speech audio and returns the text that is the transcript. Text to speech takes some text and returns speech audio that is some voice saying those words. And then there's a lot of bells and whistles and other features and things that you can have that go along with either of these processes, but at the core, that's what they do. But there are also other things you might want to do, like something called VAD, which is voice activity detection. So when you're running a voice agent or having a conversation, or even when you're just doing basic offline batch transcription, there's going to be a lot of times in audio that isn't speech audio, it's something else. So you want to know, is this segment of audio speech audio or is it not? And so that is another inference task in the space. And then there's also things like diarization. So diarization in voice AI space is what we call like the speaker identification, or like the cocktail party problem, or the speaker identification problem. So let's say you have multiple speakers on one audio recording, and they may even overlap each other. But even if they don't, you want to be able to know who is speaking. So this is almost like another feature on top of vocal activity detection. And often they are like close together in the pipeline. So one just says like, is this speech at all? The other one says, who is this? So you can imagine either combining them into joint inference, or you could do them in this like a pipeline. Like first you say, okay, this is speech audio. Now I'm going to send these into a downstream inference that's going to start assigning identities to each one, knowing that like there may be repeats. All right, check the Q&A. So nothing right now. You guys should definitely feel free to ask questions in the chat as I go. All right. So those are the main use cases. Oh yeah, and actually, these are the main ones, but there's also other things maybe coming down the line. Like you can imagine, as we get closer to speech, and we want to extract more information out of the audio, there's going to be some kind of inference around emotional content for both speech to text and text to speech. And the idea here is that when you just go from speech to text and all you have is the transcript, and then you send that into an LLM, the LLM doesn't know how the user said it, which can make a big difference. Like, what did they sound sad? Did they sound happy? What kind of inflection did they use? Did they ask that as a question, or like, did it sound rhetorical or not? All this stuff is embedded in aspects of the speech audio that aren't in the transcript. All right, I see that my screen keeps going away along the way, so I guess we'll just deal with that and I'll just keep resharing. All right, let's see, we have some questions. What is ASR versus STT? So ASR, you might imagine, like, to be honest, there's not, I don't think I've heard like anyone really get into like the weeds about what exactly this means, but they're essentially interchangeable. ASR, you might imagine, includes these other things like VAD and maybe diarization, right? Because it's a more general term, automatic speech recognition. So it's sort of like the higher level process of taking in speech audio and then processing it. So maybe it includes everything here that's not on the text to speech side. So, basically everything but text to speech. And then speech to text, usually when you say that, you're referring specifically to a model that's doing that, and you're not necessarily referring to VAD or diarization or these other things. But in the end, it's not super important. All right. Question for later: does Modal handle video streaming and tool use? Yeah, we'll come back to that one. Best practices when you want each component of a modal deployed voice agent. Cold storms, different concurrency, blah, blah. Okay, so this basically is like, how do you run we're going to get into this. This is like a lot of the talk is answering all of these questions. So Emil, these are all honestly very on point questions, and they map very closely to the outline of what we're going to go over today. So just it's coming down the line. How to handle barge-in. George, can you respond with what you mean by barge-in? How can latency be reduced in diarization normally? It takes time on SpeechFrame. Is there any library that does it? I am not sure what the latest and greatest is on diarization. NVIDIA has been releasing a lot of models that can do real-time diarization. I think it's a space where we're still waiting for maybe really good low latency with quality. If anyone has any ideas or has any experiences with diarization models or services that they want to recommend in the chat, feel free. I don't have a great answer there, but you should check out things like PyNote and the NVIDIA models. What packages or models do we suggest for VAD and diarization? Okay, so we just talked about diarization. Again, like PyNote, the NVIDIA open models are the ones I know about and are pretty good. But things change very quickly. It's, a lot of these things, I think, you still want to try a couple because different use cases might work better with different models or different services. And they all are going to have their own strong points. And for VAD, Solero really is the state of, it just kind of, everyone uses Solero VAD in general. I don't know of too many other options. Some models have VAD built in which case you don't have to worry about it. But another thing here, actually, we can mention is there's also turn-taking models. So you can identify when there's speech audio, that's VAD. But for example, I might take a long break like that. And when I do that, we don't want the bot to respond in that break as if I'd stopped talking. We want to know the difference between a break in audio. So maybe the VAD says there's no longer speech audio, but that doesn't mean that the conversational turn is over. So there's also turn-taking models. PipeCat has a really good open turn-taking model. Yeah. We are spending $1,400 on all of these services. How can we help with minimizing costs? Okay, so right now this person, Waleed, is using APIs like DeepGram, Cartesia, LiveKit, self-hosted agents, and they want to know if the cost would be cheaper. So it very much can be on Modal, but it depends on your load, right? So there's a world in which using the APIs and things like that is going to be cheaper and better. And it's maybe when you're starting up and you don't have that much load. As your load goes up, it makes more sense to run on Modal. That said, I think this is something where I would try it out. I should also mention you all are welcome to ask questions in our community Slack. Here, let me put a link to that in the chat. And there's a voice channel there, and I'm in that channel. And so you're very much welcome to post there. Sorry, I'm pulling this up. Modal Slack. And to talk about, get more into your use case, Waleed. It's hard for me to answer, exact numbers, but it is very possible. That said, for the agents, we found that like LiveKit agents, it's better probably just to go with LiveKit Cloud. If you want to switch over to something, a PipeCat agent, that you could run on Modal. All right, so here is the Modal Slack link. I'm gonna throw it in the chat. Oh, Felicia already did it. She knows what's up. All right, noisy, deconvoluted audios. Okay. So that one is a little bit outside the scope of Modal. A lot of agent pipelines, frameworks, like LiveKit or PipeCat, have modules that can be configured to use different audio filters, and that's going to be sort of the weapon of choice here, is to do some kind of like old school standard audio processing. So you're going to do like noise reduction or other sort, basically some kind of DSP on it, and then you're going to use a model that hopefully is going to be best for your particular use case, or like whatever kind of degradation you have in your audio. Some are going to perform better on others, and so that one it's a tough one, but I feel like the models are getting better and better at this. But yeah, I think it's just traditional approaches there. All right, what about memory agent remembering stuff? Okay, so again, like LiveKit, PipeCat, they're going to have context management built in. And so this is something that is, pardon me. So actually, yeah, maybe I'll take a step back. Almost all inference APIs, like your LLMs or for voice, STT, TTS, they're stateless, right? All the state is embedded, like, so for an LLM, all the state is embedded in the context, and you send the full context every time. And it's your job, potentially, unless you're maybe like using some kind of like, maybe the API provides you some kind of session to manage that context and then send it back and forth with the LLM requests. So in that sense, any sort of like agent memory strategy or pattern or package that you might use with your agent would work here. It's almost like a bit orthogonal to the voice part of things. Can you cover the eval about it? I'm not actually going to get into the evals because that is not something I'm an expert in, but I would recommend checking out companies like Coval or going to artificial analysis and places like that. Also, there is the Hugging Face Open ASR leaderboard. So here, I'm going to throw the ASR leaderboard in the chat. All right. Let's see. I'm going to take a couple more questions, and then I'm going to move forward with some of the talk content. Right. Yeah, we're going to. Okay, so data transfer from S3. How do you solve terminology error in STT? All right. So yeah, let's come back to these. I think we'll move forward with the talk for now. But if your question is in there, I will get to it. All right, cool. So, and this actually relates to some of your questions. So before we get into some of the patterns, we're going to talk about the metrics. So what metrics are important? So it's actually going to be, the same metrics that are true for most inference use cases. We're going to have quality, We're going to have latency, although this one is going to be of particular importance for the voice use case. And a lot of you are already asking about it. And then we're going to talk about throughput. And throughput, by that, we're going to mean like for a single GPU or for a single server, how many requests can it handle simultaneously? So this is also like called concurrency. And this one is tricky for voice AI, and I'll get into some of the details when we talk about model hosting. But it's one to keep in mind, but most people are most concerned with quality and latency. All right, and so we'll reference these throughout. All right, cool. So now we're going to move on and talk a little bit about some common patterns in voice AI. All right, so the first one is going to be offline or like batch processing. And this is a pretty simple use case in the sense of infrastructure. And it's something that works very well on Modal. And so I have a diagram of what this pattern looks like from a blog post that I wrote. So let's do this. Cool. Felicia, do you know why it keeps closing my shared screen? What if I do this and I just share the window? Maybe this will be more robust. All right, cool. Sorry about that. All right. So in batch transcription, in this case, we have a bunch of audio files that are stored on some volume somewhere. So in this case, we have them stored on modal volumes. Modal volumes are in uh, the remote storage part of our platform. But this could also be, say, an S3 bucket or something like that. And then what we want to do is we want to transcribe all of the files on this volume as fast as possible. And so on Modal, we're going to use we're going to write a function that does transcription on a batch, and then we are going to map over those batches. So in this case, we're going to kind of do batches of batches. And that's because our model here, our model down here on the GPUs can transcribe multiple audio files at once. But then we want to parallelize over GPUs. So we've got two levels of batching going on. And let me put the link to the blog post that gets into the details in the chat. Cool. So it's fairly straightforward. And why this works really well with Modal is that you can scale up all at once and parallelize across GPUs at runtime. And then those will scale back down to 0. And what we find when you use this pattern, let me copy this other image. Take this one over here. Boop. Right, so what we find is that on Modal, if you look at the throughput, so this is going to be in audio hours per second versus cost, you can see it's significantly cheaper than using like a proprietary API. And the reason for this is because when you call out to a proprietary API, there's a lot of other users, there's a lot of like sort of intermediary things going on your request that help them manage their load. And while that, is very useful for their sort of like P50s, it's not great for their P99s. You also can't necessarily batch in the same way on these models, where you can ensure that all your audio files are being sent in one forward pass on the GPU, whereas we can do that with these open NVIDIA models. So here we're using Parakeet and Canary, and these are a bit older. This was done quite a few months ago. But so for batch transcription, using serverless infrastructure like Modal is a great choice. The word error rate of the open models is very competitive, and the cost and performance are much better. Do I have one more thing? Yeah. So while we're here, I'm going to call out one little detail that's worth knowing about when you're doing batch transcription. And this is like getting a little bit in the technical details. All right. All right. So when you create batches, and this actually goes for any batching or sort of any parallel data processing. Actually, this is actually a general principle. But what we're looking at here is when you send a group of audio files to be transcribed in a batch on the GPU, meaning that they are sent as sort of one GPU request. So your model or your inference engine can handle true batch processing, true parallel processing. When you do that, you want to make sure that all the inputs in the batch are going to take the same amount of time to process, because that batch, because it's one call, it won't end until the longest element in that batch is finished. So for audio processing, this often means sorting by duration, because the model is going to move forward over the audio file when it does inference. It's not, it doesn't take it all in at one big chunk. And the inference time for speech models or voice models is usually going to be proportional to the audio duration. And so you want to sort them and make sure your batches have audio files of the same length. Otherwise, you get all this dead time and you have these empty lanes. And this is actually like, for example, for the experiments we ran in this blog post, this was actually like one of the most essential things we had to do to get performance up, even though it's not like something super fancy. All it is, you sort the files, you batch them in order from there so that all the files that are near each other in duration end up near each other in a batch. All right, cool. All right, so I'm gonna look through the QA and see if there's any questions specifically about the batch stuff real quick. All right, so there's a question about statefulness and things like that. We'll talk about that when we get to the voice agent use case. You say auto scaling GPUs, you mean it like a start another GPUs, like horizontal scaling. Yes, that's exactly what we mean, Mark. So Modal, that's like kind of the core promise of Modal's serverless functions and auto scaling is that you just set a few parameters like min containers, which can be 0, buffer containers, which says like help keep a couple buffers, that will keep you robust to bursts. And then as your load increases, Modal will scale up. And then we'll scale back down for you. That's right. Inference frameworks for TTS you recommend. Let's get to that when we talk about model serving. Hold on, let me check these off. Check. What is a good speech embedding model used for multiple tasks? I don't know if anything like that exists, actually, to have something that just does embeddings and then those embeddings are used for other things. Maybe it does in terms of like retrieval, but I don't know. I don't know about, I don't care about that use case too much. All right. So there is this question, what best practices to reduce latency of transferring audio assets out of modal to S3 buckets? This is sort of related to batch, in that batch is going to be our use case where we need to move a lot of audio at once or move a lot of data at once, which in serverless or distributed computing is a pain point. So the way we recommend doing this, so actually I realized this is about egress, about out of modal to S3 buckets. So Modal has cloud bucket mounts. You can use those to talk in a performant way or to send data back and forth in a performant way with S3 buckets. You could also store your output directly on Modal volumes. And we often recommend using, like if you're in Python, like some kind of thread, like thread execution for data transfer so that you can maximize bandwidth usage and not, be like dependent on some loop or some, whatever Python might just natively use to copy like a list of files, but to take a little bit more control of the parallelization of data movement so you can optimize bandwidth usage. That's like the general approach to moving data around either to a modal volume or off. Right. So if you were doing like batch text to speech where you have audio files as the output, you would, your bottleneck would be on the way out. All right. So let's move on to the next use case, which will be voice agents, which is the one that a lot of these questions are about and kind of brings us all together. All right, cool. All right, so for voice agents, they are going to look something a little more like this. Or actually, here, let's start with the basic setup for those of you who haven't seen this yet. So a voice agent or a voice bot is something that you're going to have is a AI system that you have a conversation with using speech. So you are going to talk to it. There's going to be your audio is going to be picked up by a microphone. That is going to go through speech to text, which, as we said, is going to turn that into a transcription. That transcription is going to get fed into an LLM, which is like our text to text part of the pipeline. So this could be like a foundational API or a model you're hosting. And then the response from that, some of it or all of it, depending on how you're set up, is going to go to text to speech, turn into speech audio. And that's going to play back out over your mic. In practice, deploying something like this is going to be a little more complicated. So here is an example from a blog post I did on building a voice bot, which we're going to demo in 1 second. And I'm going to put the link to the blog post in the chat. Cool. All right. So this is significantly more complicated. So in this case, pardon me, you're going to have some clients. So often, yeah, I should put it, often in the batch transcription use case, the client is you, right? Like you have a bunch of audio you need to transcribe, or let's say you have a bunch of text that you want to turn into speech audio, which is a little less common. In this case, you're probably serving some bot that's going to do something useful that is your product. You're going to have clients who are not you, who are going to be your customers probably, who are going to connect to this bot, and they're going to have a conversation with it. And that bot's going to need access to the 3 services we mentioned above, STT, LLM, and TTS. And so this is what a deployment of this looks like on Modal. In this case, the way I set it up is I have a little front end server, which is just like a very lightweight, fast API app. And clients will go to that in their browser using HTTP, and then they will hit connect. When they do that, this server is going to spawn a Modal function. So this is a Modal container that is going to be the bot. And this function is going to run, this is going to live for the lifespan of the conversation. And in this case, we're using PipeCat, but like this could also be where your LiveKit agent lives. And as I mentioned before, for now, our recommendation is for LiveKit agents to run them on LiveKit Cloud. And then you can use Modal for either like the avatar, which we didn't talk about here yet, or for these other services. We are working with them on like trying to find a nice pattern for running LiveKit agents on Modal. And we do actually have an example of this on our repo, which I'll try and put in the chat. But I'm going to be real, none of them are like perfect and do exactly what you want yet. So yeah, for now, the easiest thing is probably just use LiveKit Cloud there. However, if you're going to do PipeCat or do something, you're going to roll your own, then you can definitely do this on Modal. In this case, we're using PipeCat, and we're also going to be performing RAG on Modal's docs for this example. And so we have ChromaDB in memory on the bot as well. All right. As completely independent apps on Modal, we are going to launch a speech-to-text service, an LLM service, and a text-to-speech service. And what I mean by independent is that these apps just do the thing that they're built to do. They don't know about this bot. They don't know about each other. They're going to auto-scale independently. So this is important, right? Because this actually relates to some of these longer questions that were posted that are kind of like asking, about just this whole pipeline and how do you optimize everything? And, they're asking a lot of the details. One of them was about the different capacities of these different services in terms of throughput, right? So the number of concurrent requests they can handle at once. And so what's nice about deploying these yourself on Modal is that when you deploy them as independent functions, they just scale independently, and they can have their own scaling parameters. So for example, you might be able to handle a lot more concurrent requests using an inference engine like VLLM or SGLang with your LLM, but your speech to text service maybe you're just limited to something like duplicating the model on the GPU, and you can only do that 4 or 8 times, or maybe 20 times. And so the concurrency on that function or server might be less. But again, these are all totally independent. And similarly, we have it set up, and you can go to the blog post, you can go to the GitHub repo through there. We have it set up that for the bots, they're single-use containers. And so what this means is they just serve one conversation at a time, and then they go away. And this is like useful when we're using WebRTC. It helps keep things clean and avoid like any kind of weird issues when you have multiple WebRTC clients on the same bot. It also avoids like potential blocking issues and things like that. I'm not going to talk about WebRTC too much. I think maybe if people have a lot of questions about it, but I should call it out as like a very common part of real-time audio video over the web, and therefore it plays a major role in voice agents. So Pipecast is built by Daily. Daily provides WebRTC infrastructure. LiveKit provides WebRTC infrastructure. That's why they also have platforms for voice agents. There is a way to do this without those platforms using Pipecast and something called small WebRTC. And if people are interested in learning more about that, maybe go to the community Slack voice channel. I think I'm going to punt on the details there. All right, so let's do a quick demo of this voice bot, and then I'll look at the questions about voice agents. All right, so here it is. I think you guys can see that. Cool. So let's see. It takes a couple seconds to spin up because we have to establish our WebRTC connections and do some handshaking. Also, some of you were asking about cold start times. I hopefully will have time to talk about strategies there, but I want to just call out because you asked that there's min containers equals 1 on all my services here. So there's no cold starting. All right, so here we go. Hopefully this works. All right, here we go.
You can create and use volumes to save. Modal supports interactive widgets and use the file viewer to browse, upload, and download files. Changes appear instantly. Your notebooks with teammates or anyone via public link. Volumes let you save data that stays across
let's
sessions.
Start over. Can you just show me how to deploy a simple Python function on Modal?
To deploy a simple Python function on Modal, first define the function in a Python file, and use the Modal deploy command to push it to the cloud. The function runs in a secure container and scales automatically.
What if I want to add a GPU to my function?
You can add a GPU to your function by specifying the GPU type in the function decorator. Use GPU with a value like A100 or H100 for a single GPU. For multiple GPUs, use H108 for 8 GPUs.
Are there any examples that show how to use Modal with WebRTC?
Modal does not currently support WebRTC directly.
Oh no, I got that one wrong. It should have access to the examples. All right, so we'll stop that. So actually, let's talk about what happened at the beginning there, because this is a good call out. So what happened is that it started to say its intro, which is supposed to say here, it's like, hi, I'm a voice agent. I'm here to help you build on Modal. But immediately I was talking to you guys, and I should have muted this so that it didn't go to the voice bot. But I said, all right, here we go. And then that input, it didn't really know what to do on. And this is more because this app is not like super optimized to do exactly the task it's meant to do and handle all edge cases. It's more about demonstrating how to get low latency voice agents running on Modal where you're deploying all of these. So that was just running off these exact deployments. It was over WebRTC sending my audio. That was making a round trip to the speech to text, making a round trip to the LLM, and making a round trip. So all of that happened, and then it played the audio, and then it sent the audio back over WebRTC, and then we all heard it. So all of that happened in about a second. But because I spoke and it heard it, that triggered the interruption signal in Pipecast. And then it tried to respond to this. And like I said, it didn't actually know what I was talking about. And so it, for some reason, started talking about volumes. All right, let's see. All right, so I'm going to take a second and look at the questions about voice agents. All right. Does Modal handle video streaming and tool use? So, okay, now that we're at the voice agents part, I was kind of waiting for this. So one, this can handle video, and I don't have an example, but if you here, I'll put our general WebRTC example, which does exist, despite what the bot said. Usually I ask questions that I know it'll get right. I'm not going to lie to you because again, that demo is more about like the infra and not about the performance. So, you know. All right, here's the WebRTC example. This shows how to set up WebRTC, like not even using Pipecat or any of that, just using like AIO RTC and with video. But if you use Pipecat or LiveKit, you kind of get that for free. If you are trying to do tool calling, this is something that, as far as patterns go, is a lot more like a sort of work in progress in the field. And this is because people are trying to work out the pattern of you want the LLM to respond and send some response to text to speech to start talking and not wait for the tool call. And this is because we're obsessed with latency and time to first, byte or like time to first audio. And so there's different ways you can achieve that by implementing things at different places, like in terms of like you could do it kind of all through prompt engineering and the way you manage sending things to LLMs. But also, I know that Pipecat, and I'm not sure about LiveKit. I'm not saying they don't. I'm just not as familiar. But Pipecat for sure is thinking a lot about this and adding features to their framework that handles async tool calling. And I think that that is basically the main direction we're going to go in. Is that your LLM will give some output, the tool call will happen asynchronously, and the speech output will go forward. That speech output will be some kind of like, I'm working on it, or some response that's useful that doesn't include the output of the tool call. The tool call will return its output that sort of feeds back into the LLM asynchronously, and then it will deliver the output. Now, there's a lot of nuance here, and like, okay, well, what if the user starts talking before the tool call is ready, and now you have these like two threads? This is kind of like this is sort of like the interesting problems that people are thinking about, I think, right now in voice bot building. So I don't think there's like packages that will just solve this for you. I think people are doing things a lot of times, especially for like big deployments and like, companies who have big agent loads, they're doing things custom. But I think things like Pipecat and LiveKit are going to offer more and more features like this. However, the way it interacts with the LLM is interesting and not totally solved. All right. Best practices when you want each component of the voice agent to scale to 0. Yeah, but it might have different cold start times, different concurrency. Does the bot reserve one of the slots? This is great stuff. Who's asked this? Yeah, Emil. Okay, so scaling to 0, right? You can only bring up a container so fast, especially if you need to load a model onto a GPU. I've explored this using GPU snapshots on Modal, and I think that Felicia or someone put the cold start time guide in the chat, which should link out to that. And what I have found, and actually let me pull up a slide real quick, showing some cold start improvements like for the models in this voice bot. Give me one sec. Let's see if this copy paste works. No, let me just screenshot it then. Give me one second. I'm pulling up a graph that shows cold start time improvements. Cool. So for those models, they happen to actually be really compatible with our GPU snapshot feature. And so you see the native cold start times here, 40 seconds for SG-Lang with Qwen, 90 seconds for Kokoro. It's something like 22 seconds, 25 seconds. And we bring those all down under 10 seconds with GPU snapshots. However, 10 seconds is still like outside the range of what people would consider okay for like connecting a call to a voice agent. So what I have played with is the ultimate solution here looks something like this. Okay, one second. I'll do the screenshot approach again. And in fact, you can see this slide is even titled exactly what fast, minimizing time to first speech when scaling from 0. So the ultimate strategy looks something like this. The client connects to that front-end bot node. I keep the front-end bot and the bot runner, I keep a warm container of each of those because those are CPU-only nodes. And so it's quite cheap to keep one live. I also use GPU snapshots, which brings the startup time down for each of those to be under 3 seconds. So that way, if you do fall behind your buffer, you're not waiting that long. But because the cost of those is cheap to keep them live, that was, we're trying to sort of balance cost and performance here. I did that. I think, hold on, I have it in the slides what that cost an hour. Let's see. Yeah, it's 11 cents an hour to keep these two warm. For the speech to text LLM and text to speech, I showed we improved the cold start times, but that's out here. So what I did is that in the bot runner, what I mentioned before, right? It started to do this intro that it always does, where it introduces itself. So I just recorded that, and instead of prompting the LLM to generate the same thing every time, I just play that out right away. It doesn't require any models, just an audio file. And it takes about like 10 seconds to 15 seconds for that audio to play out. One of a general strategy that can be useful in these voice bots is doing stuff or taking the time when the bot audio is playing. So for example, if you have a long response that's many sentences, you want to get that first sentence out to text to speech right away from the LLM because the LLM output is streaming. Get that first sentence playing, that maybe takes 10 to 15 seconds. In that meantime, you could generate a lot of text output from the LLM as well as the audio from the text to speech. So getting that first little sentence playing is really useful. Whether you're doing this canned intro thing or just in the general turn taking process. So in this case, because we have this canned intro, as soon as the bot runner is running, even before it's established connections with any of these services, before these containers exist, it's playing. That covers our time to do these fast cold starts. That said, I don't think this some models don't cold start this fast. Sometimes you're running multiple GPUs on one container because you're serving many models or something like this. Those are going to be slower to cold start. So this is like a very good outcome. I don't think it's always going to be the case that you can scale to 0 and it's just going to be easy to make it feel perfect. But that said, Modal is one of the few places where you can do that. And it's one of the few places where you can do GPU snapshots as well. So it is on the table, but not always. All right. I hope that answered your question, Emil. If you want to follow up, yeah, I go to the community Slack. All right, cool. Is this demo available for testing out? It is. I posted a blog post in the chat, which links to the GitHub repo. All right, I suppose that translation is easy, says Willie. I don't know. The one thing about translation is that you can't really stream it because the order of words is not going to be the same in different languages. So that kind of limits some of the strategies we use. All right. Inference frameworks. Okay, yeah, we have 10 minutes left. I don't see any other questions about voice bots per se. So maybe we can quickly talk about serving models, and that will allow me to talk about this inference framework question. So one of the other use cases is serving a model. And so for example, the customers we see that are doing this are the ones that are developing their own models. That said, maybe you want to host a model for a voice agent or for some other use, but you don't want to use an API. So for LLMs, this is easy. We have things like VLLM and SGLang. All of them are based around more or less the same architecture. And so adding a new model to an inference engine is not that much work, compared to if the whole model architecture wasn't available. And for LLMs, we do have this idea of continuous batching that's sort of solved, where we can have multiple different users streaming requests in and out, and the LLM, the transformer is ticking away step by step. And some of those steps include requests from some users, and there are different ways along, different steps along in generating the output. And you can just interleave them. And so that's pretty easy. For speech, this does not exist, and this is a major pain point. There are no general purpose inference engines for voice models per se. There is SG-Lang diffusion and VLLM Omni. And so for some models, this will work, but there's more overhead in getting these models into the engines. But for example, I think like the Quen models tend to contribute to VLLM Omni. There are also models like Nemotron, the Nemotron speech model, which sort of has an inference engine built in that it can also handle asynchronous streaming input from users and produce the transcript. The other options you could consider are something like Triton Inference Engine, which has the ability to just duplicate the model across the GPU and then handle serving those. One thing I should call out is that becomes often less compatible with GPU snapshots, but that's not necessarily a deal breaker, especially if you're in the high concurrency case. It means you probably have big load, which means scaling to zero might not be necessary. And I have implemented this, for example, with Kokoro TTS, and it's definitely worked and given me a speed boost, in meaning that I can concurrently create audio for multiple users, and it doesn't scale linearly with the number of users, it scales sublinearly. All right. Link to the cold start figure. That is internal for my own speech, for my own talks. I don't know if this is external anywhere yet. But you can get, it's not too hard to implement. And in the voice bot implementation, we have GPU snapshots set up, so you can test it there. Are there any other questions? All right. If not, I'll call out another thing about hosting your own models, which is that another option here, depending on what scale you're at, is to self-host a proprietary model. So for example, you can self-host DeepGram on Modal, and they're in their documentation. Here, I'll post a link in the chat. They have information on how to do that. Okay, yeah, actually, wow. Sarah or Sala just asked before this, is it possible to use non-open source TTS and LLM models? So LLM models, I don't know if there's any LLMs that allow you. I mean, I guess a lot of them do. I don't know if anyone does that on Modal. I think it's mostly when you're on Modal, you're using open source. And I should call out that we have a whole LLM inference product that is going to be released soon. It's already you can already use it. There's already some documentation about it, but it's not GA. But part of that is auto inference, where we'll help you with spec deck. So that's a way to use an open source model, but improve it so you start to get really competitive performance. But for open source, non-open source TTS and LLM, not sure about LLM, but for TTS, you can definitely use DeepGram. You just have to have, get the self-hosting license with them, and then follow these instructions that I just posted in the chat to deploy that on Modal. And in fact, I think the Modal part, you don't even need to get in touch with us, but you're welcome to. We're happy to help. All right. Talk about duplex models, speech to speech. So my take on this, yeah, so I'm glad you called it duplex, because I don't think pure speech to speech is ready, nor do I think it's necessarily what we want. You often want to have access to the text outputs to do all sorts of other things like tool calling. I think that a better way to think about it is there will be many modalities that'll be interacting at one time. And how you organize that across models is up to you, and that we will want the flexibility to organize that across all models, and that any single model that claims to be doing it all sort of end to end, like a speech to speech model, is probably doing a lot of this under the hood and then giving you parameters to it. I don't think like we do want modularity. We do want to be able to sort of access IO in the pipeline along the way, not just at the beginning and end. That's my personal take. But I do think, for example, Personaplex or especially Moshi-based architectures are very good. I think the work coming out of the Kayutai group, which now has their commercial Gradium offering. So if you go to Gradium, that company is built out of Kayutai. I think they're doing really, really great work. All right, so that's speech-to-speech stuff. Which workaround could fit with an outbound lead gen setup where usually speakers first? Yeah, so that one. So okay, so in that case, what I would imagine is that you're just buffering that audio, so you allow them to start speaking. And I think Pipecast even has this built in. Maybe could be wrong about that, but basically, I would just buffer the audio and then process it all at once your downstream services are ready. But I can already imagine some ways in which that experience might not be great or like confusing for the user. You might need to still indicate to them that you're not totally processing it yet, so they're not like what's going on, or keep talking or something like that. One thing I did is I implemented a pre-recording that just said like stand by, like we're still setting things up, and then that you could have that just as text on the screen, but in this case it was audio, so it feels more like the bot is talking to you. All right, is that demo available? We changed that spot. All right, cool. So we have a few more questions, or sorry, a few more minutes. If there's any other pressing questions that I can address. All right, I'm not seeing any new questions. So hang out for one more minute, but if not, thank you guys for listening. I appreciate you working with me in this more like freestyle format of questions and whiteboard. I hope you found it useful. And again, we have we have like a voice and audio channel in our community Slack, and that's the best place to follow up with more questions um, or yeah, more questions. All right, cool. Well, thank you everyone for listening. And yeah, like I said, see you in the Slack.